Welcome to The Explainer. Today we're looking at something that completely challenges the very foundation of how we evaluate artificial intelligence. We tend to treat AI scoreboards as absolute truth, right? But what if those objective scoreboards we use to evaluate these massive models are actually fundamentally flawed? What if the yardstick itself is broken?
Think of it like the ultimate detective mystery. There are literally billions of dollars in AI investment and just massive engineering efforts, all being driven by how well models perform on these standardized benchmarks. But we have to ask, what if the AI isn't the thing failing? What if the test is? Today, we are questioning the reliability of the very datasets that tell us which AI is the smartest.
Okay, let's dive right into this because there's a truly shocking anecdote from our source material that really sets the stage. There's a widely used mathematical reasoning benchmark called GSM-8K. Now, the model DeepSeek R1 originally ranked near the bottom of this test, the third lowest to be exact. But after researchers systematically revised the test to fix broken questions, DeepSeek R1 absolutely skyrocketed. It became one of the top-performing models, landing in second place. Think about that for a second. The model didn't actually get any smarter. The test just got fixed. It shows exactly how broken test questions can severely distort our entire understanding of AI performance. So, here's our roadmap for solving this mystery. We're going to cover the broken AI scoreboard, Stanford's fantastic bugs, testing the test with math, the two-step bug catcher, real bugs in the wild, and finally, the future of AI tests.
All right, part 1, the broken AI scoreboard. Let's look at why these benchmarks are flawed.
The core problem with maintaining these critical AI datasets really just boils down to sheer scale. Take the famous MMOU benchmark, for example. That test alone contains 14,000 questions spread out across 57 specialized domains, ranging from chemistry all the way to philosophy. Manually reviewing every single item in these modern benchmarks using human experts is just prohibitively expensive, and it takes way too much time. Because of this massive bottleneck, most benchmarks are rarely, if ever, revised after they're released. They basically just sit there, quietly accumulating undetected errors. Moving on to part 2, Stanford's fantastic bugs and the push for systematic test revision. This explainer is actually based on a brilliant paper titled Fantastic Bugs and Where to Find Them in AI Benchmarks. The lead authors, Sang-T Truong, Yuheng Tu, Michael Hardy, and an incredible research team out of Stanford University took on the monumental task of creating a real framework for systematic benchmark revision. They didn't just want to spot fix a few random questions. They wanted to build a highly scalable system to basically clean up the entire industry. Part 3, testing the test with math. Let's get into the measurement-theoretic side of things. So, to hunt down these bad questions, the researchers turned to psychometric research and a concept called unidimensionality. Sounds like a mouthful, but let's break it down. Imagine a classroom of human students taking a math test. If the test truly measures one core ability, like math skills, then a student's total score is a pretty great summary of their ability. Because of that, we can accurately predict how a normal question should behave statistically. If a student gets all the incredibly hard, mind-bending calculus questions right, they should probably get the basic addition questions right too, right? If a question starts defying those expected patterns, something is definitely wrong. So the crucial takeaway here is this. The Stanford team used this measurement-theoretic math, specifically things like tetrachoric correlation, to map out exactly what normal item behavior looks like. When a question's statistical response patterns start falling way outside that expected range, when it acts as a statistical anomaly, it basically becomes a smoking gun. It flags the item as potentially invalid, meaning the human experts now know exactly where to look. Which brings us to part 4, the two-step bug catcher. This is where the automated investigation kicks in. The Stanford team didn't just stop at the math, though. They brilliantly divided the labor into a highly efficient workflow. In step 1, the measurement-theoretic math scans thousands and thousands of questions and flags those statistical anomalies. It finds the needle in the haystack. Then, in step 2, an AI deputy, which they call an LLM-judge, does a first-pass review of that flagged question to categorize the exact type of bug and provide a short, logical reasoning. Now, what's really fascinating about this process is how a frontier AI model acts as a classifier. The original question, the answer key, and the AI's responses are all fed into this AI judge. It then determines if the question is valid or invalid. And if it's invalid, it sorts it into specific categories and actually outputs a concise justification for why. This is a game changer because it means human experts only have to verify the AI's reasoning rather than starting completely from scratch.
It drastically reduces their workload. This AI judge is specifically hunting for 3 distinct culprits. First up, ambiguous questions, where the wording is just so vague it allows for multiple valid interpretations. Second, outright incorrect answer keys. And third, and this one is absolutely vital, grading issues. Grading issues are incredibly hard and super costly for humans to detect manually because you basically have to check the AI's actual output format against these really rigid automated rubrics. For instance, if an AI answers 4.00 but the rigid grading system only accepts 4, the AI gets marked wrong even though it's mathematically completely correct. It is almost funny to think about a billion-dollar supercomputer getting completely defeated by a grading rubric just because it added a decimal point. But the LLM-judge is absolutely perfect for spotting these kinds of semantic equivalence.
Section 5. Real bugs in the wild. Let's see how this framework actually performed. When the system was deployed across 9 widely used industry benchmarks, the results were honestly phenomenal. When the framework flagged questions based on those statistical anomalies and human experts came in to verify them, up to 84% of the questions flagged were confirmed to be genuinely flawed. That is wild. This isn't just statistical noise. This is an incredibly precise radar for bad data across datasets ranging from medical reasoning all the way to high school math. To give you an idea of how insidious this can be, consider the TIE exam benchmark. During the creation of this specific dataset, an optical character recognition, or OCR, error mistook a visually similar TIE numeral 7 for a 3. Just one tiny little glitch, but it completely changed the meaning of the passage and completely invalidated the answer key. This is the kind of flaw that non-native speakers, even if they were using translation tools, would probably never ever catch. But the statistical math caught the weird response patterns and flagged it so native-speaking experts could fix it.
And the crazy part? This system actually gets stronger at scale. The precision of catching these bugs drastically improves when you increase the diversity and the number of AI models actually taking the test. Think about it. If you only test a few similar models, they might all just make the exact same mistakes. But when you use a really large, diverse pool, say 60 to 80 different LLMs from various organizations, the statistical anomalies become so much clearer, raising the precision of the bug detection significantly.
Finally, Part 6, the future of AI tests, and why continuous stewardship is the answer.
This Stanford framework fundamentally changes how the tech industry is going to evaluate models from here on out. It matters because we can literally no longer assume a benchmark is perfect just because it was made by domain experts. We actually have to infer the test's quality from how the test takers behave. The researchers are advocating for a massive cultural shift in AI, moving away from this old publish and forget mentality and toward a real culture of continuous benchmark stewardship. We need to actively sample AI responses, clean our data iteratively, and build robust guidelines that implement the statistical framework before new tests are even released to the public. Which leaves us with this final thought. If flawed benchmarks are deciding where billions of dollars go, and they're artificially holding back models like DeepSeek R1 because of grading glitches and OCR errors, then as AI gets smarter, are we finally ready to start testing the tests? It's a completely new landscape for AI evaluation, and ensuring our yardsticks actually measure what they claim to measure is really the only way forward. Thanks for joining me on this explainer. I really hope this sparked your curiosity about the hidden mechanisms grading our most advanced technologies.